Hello, in this presentation, I'll be making an interesting use of graph search algorithm for the problem of motion planning for multiple autonomous vehicles. The introduction of the problem description is in a separate slide which the video description should guide you through. Now first of all, we are using the concept of graph search, and as we all know, graph search algorithms are optimal and complete, so that's the best choice that you can have. The only problem is, in order for them to be optimal and complete, they have to be very slow. The computational complexity is very high, and so all I'll be doing out in this slide is I'll be solving out this problem of computational complexity, and the way I'll be doing it, I'll be very selective in which states get expanded. I'll be very selective in what all child states that they produce, and if you know that you do not expand all states, if you know that you produce in only a small subset of states, then you get a very small graph which the graph search algorithm can solve within no time. So I'll in this presentation be very selective in what I expand and what I produce. Now, as the title of the presentation states, using a notion, I'm redefining the notion of lanes here. We all know, if you have watched the introductory video, that the problem is for solving for a traffic which has no lanes, where there is a completely chaotic traffic, a very wild kind of traffic. So I say that if I need to insert in a concept of lanes here, keeping all sorts of chaotic motions possible, how would my lanes be? And these are the properties that I came up with. The first thing, that they are distributed. So if this is my any general road, suppose there are 3 vehicles out over here, suppose there are only 2 vehicles out here and there is 1 vehicle out here, so we can nicely say that this segment of the road consists of only 1 lane which this entire vehicle is occupying. It can do anything in this lane. Here there are 3 lanes. One is like this, the other is like this, and the other is this entire region out here. Here there may be only 2 lanes in this narrowed section. So it's a very variable kind of definition of lanes, where the number of lanes, they change as I go along the length of the road. In fact, they do not only change as I go along the length of the road, they also change if I move across in another dimension known as the dimension of time. So suppose this was the scenario at some time. This was, let's say, a very fast moving vehicle. So what would happen out in the future, if this was a very fast moving vehicle, it will soon be a scenario like this, where those 3 vehicles are out here, and let's say this 1 vehicle is out here. So I've got only 1 lane out here, and this vehicle came in here while all these vehicles moved ahead by some amount of time. At the other time, what will happen, it will join this pool of vehicle out here. So I'll have 4 vehicles out here. Let's say this vehicle joins in here, so this one is this vehicle. Then this vehicle will come here, so there will be 2 vehicles ahead, and it will finally overtake all these vehicles out ahead here. So my definition of lanes, it changes along the length of the road, it changes along the length of the time. At any time, there's only a single vehicle that can occupy the lane. A single lane can be occupied by a single vehicle, and of course they are variable width. So I've got a nice big truck out here, I've got a nice 3-wheeler out over here, there's a cycle out here, and there's another nice car out here. Now this distance will be much less than this distance, and this distance might again be much less than this distance. Bicycles move in, so in order to make this clear, let me fit in another bicycle out here. So this is a very small lane and this is a very big lanes. So they are variable width. I'll have concept of small lanes, I'll have the concept of wide lanes. and that's how you can visualize that the very chaotic kind of traffic, the very unorganized kind of traffic, we can insert in some concept of very flexible kind of lanes out in that traffic, and that is what will be used as the basis of this presentation. Very flexible, very dynamic, very distributed lanes which all have different widths. Now I won't be explaining in this presentation what is a general graph search out here, but I've used this variant of it. I've used a uniform graph search, which is a very general kind of graph search which starts from the source, keeps expanding in states until it comes to the destination. Of course, I have got the problem here that there are too many states and there are too many actions, and as I said that I'll be very selective in what I expand and what do I expand to. That will solve the first part of my problem, which is the problem of planning, wherein I take in only one vehicles. The other problem is the planning of coordination. If I go by this approach, the graph search algorithm is only valid for a single vehicle. So after I solve this planning problem out here, I'll solve this problem out here where I'll plug in some aspects of coordination into the algorithm. And this is the general principle that I will be using. I've been saying that I'll be very selective in what I produce to. I can only do that when I have some hypothesis with me. So my hypothesis would be a very nice driving phenomena where we know if I am here, there's an obstacle out here. If I need to overcome this obstacle, so I'll select in the mid of the road, which is the widest segment possible. So I'm trying to maximize my lateral separation from the obstacle and the road boundary. That's what always happens. But obviously, if this obstacle was very thin, it was only an obstacle out here, I won't be traveling to the center of the road now. It'll be a waste of space, it'll be a waste of separation. So in order to make my driving good, what I'll do is that I'll drive like this, keeping only the required separation, giving a very large separation that's only more than a threshold. So we always maximize our lateral separation and we prefer to drive as straight as possible, making in the least of lateral deviations here. Now I assume that the general graph search methodology is well known to the viewers, so I deal with, if it is not known, that will not make much of a difference, except for the fact that I won't be presenting what a graph search is. For those of you who are not well aware of the uniform graph search, can only think of it as a problem that I need to define a graph which has the minimum number of states and the minimum number of edges. If I define this graph, then the problem of graph search is a very conventional problem which can be solved. So this presentation lies only at the stage of definition of a graph. For those of you who know the uniform graph search, obviously would know that if in a graph search I have a state L which has been produced in some ways from the state, from the source state, the problem is in what edges do I add to produce in my new set of child states, which ultimately produce the entire graph search fundamental. So I'll be dealing with only this problem out here. I won't be dealing with anything else in the uniform cost search or any other graph search for that matter. It is taken as it is in the general problem solving methodology. Of course, I'll be breaking down my problem into two parts. The first part would say, don't think about any other vehicle, just think that there is a single vehicle in the road scenario. And later on, I'll be extending this solution to the fact that there are multiple vehicles, which will be the problem of coordination in how do I coordinate between multiple vehicles. So this is just the first part of it, where there's only a single vehicle. And my solution to this problem is extremely simple. My solution just says that there is a road that is given to me like this, which has some obstacles like this and like this. All that you need to do is if I start my planning algorithm from here, all you need to do is taken a sweeping line, pass it across all these obstacles right here, and for every such pathway which is bounded by a road or an obstacle from both these sides, select in which will be my best position. So if I'm traveling from here, my best position would be right here. Again, I do not, it's a wide road, I do not want to go very far away, so let's say my ideal position is right here, it's right here for this region. I will not be able to fit here, so I'm not expanding this state. I would not have been able to fit here, so I did not expand this state. It is right here. Here I can fit in, let's say, so it's right here. For both these regions, it will be the center of the road. At this stage, here I have got an option here, I've got an option here, so it will be both these states. Again, the center of the road, I can fit in here, I can fit in here, and I'll nicely extend up this graph into all the various states possible, which will produce this kind of graph. And I'll basically use a simple graph search, as I said, to find out which of the path is better. So let us say the path that was better as per my distance metric was this path graph out here, and this will become my trajectory that I follow. So the solution is that simple, except for that we know that there will be a slight bit of problem out here. If I've got my obstacle like this and some obstacle here, if I start from here, my first scan, let us say, is this, and subsequent scans are something of this sort. My first selected point would be like this, which is the only point possible. If I extend my graph out here, now my car is facing right next to the obstacle. It can neither turn right nor it can turn left. This in fact the same problem which I highlighted in the introductory video. So this may produce my vehicle very close to the obstacle. The problem is that we are maximizing lateral separations. We are not maximizing vertical separation, or we are not maximizing longitudinal separation. So I've got a nice little graphic out here which says how do I solve the problem. Again, I've shown only one instance of the line sweep out here. So this is what was my sweeping line as in the previous presentation, and the problem was that in this I had to identify regions. So let's say these are all the three red colored regions possible out here. I select this point out here, this point out here, and this point out here. Now I know that if I select this region out here, there might be a very close obstacle right out here, so I will not select this region, but rather I will select a region at a different line before this point. And similarly, if I select this region out here, I'll transfer this point here. If I select this point out here, I'll do only one thing, I'll transfer this point out here. So these three are the points that I have selected based on my obstacle analysis. This line can be called as obstacle analysis line, and these are the mirrored images at a nearer line that I will be actually using for my trajectory generation and my actual movement. And if you are clever enough, you can basically see that earlier my problem was I was maximizing the lateral separation and not the longitudinal separation. So now I can be assured that this is the least longitudinal separation that will always be guaranteed. So I have solved the problem that I am now maximizing both the lateral separation and my longitudinal separation have been set to some nice big threshold. And suppose in that scenario I select only one of the points, that is point out here. Its mirrored image was like this. My disk trajectory will be actually traced by some vehicle, so I use a nice smooth clothoid curve out here. It needs to be obstacle free. I check in for feasibility of this point. While this is an point that the curve joining this point to this point, that means the actual point that came by obstacle analysis, and my actual point for trajectory generation, that is only checked for trajectory, it will not be traced by the vehicle. So out here what you see is that there are 2 points. This is traced by the vehicle, this is not traced by the vehicle. In the next iteration I'll have my line like this. This will be the selected point. this line now would be the actual points for, I'll mirror out this point out here. This trajectory would now be generated by the vehicle, while this will be only for computing the analysis. There'll be subsequently a trajectory out here. So that's how my curve would extend, or my graph would be produced in a similar methodology that we stated before. And this shows how the entire graph is produced. Now there are some lines that you obviously do not see. My vehicle could not fit in here, so there's no line like this. Here there's a nice, in fact a dirty little crisscross. The problem is that this was my obstacle analysis line. It selected 2 points out here. The point was mirrored out here like this. And now when the obstacle line, analysis line was shifted, in the next iteration of the graph search graph producing algorithm, then it noted that even this was possible. So there's a dirty crisscross out here, but the basic intention is only to produce graphs like this. And what I have produced are the clothoid curves, so they are smooth little paths. And this methodology that I presented so far produces nice result, except for one problem. The first problem I introduced was that I could be too near the obstacle, because of which I had to take a different obstacle analysis line and a different line that was before for the trajectory generation. Even that creates a little bit of problem. Suppose I am here, there is an obstacle out here, my obstacle analysis line is this. It sees that there is nothing possible. It tries to connect, it mirrors out this point out here. It tries to connect this using clothoid curve and this by a normal line segment, and this will never happen because there's an obstacle out here which is so small that my obstacle analysis line completely missed it. My obstacle analysis line moves in some distances, so it completely missed citing this obstacle. And no matter how hard I try, I'll not be able to construct a feasible trajectory because this obstacle got completely missed by the obstacle analysis line. And we know that if the obstacle analysis line that is hopping in steps of delta, if it completely misses an obstacle, there's nothing that can be done. So if this problem would be discovered if a point is selected but I'm unable to find a feasible trajectory that connects my point, that connects these 2 points via clothoid curve in the first half and a normal line in the second half. So when I discover this problem, the solution is very simple, that I need to make my obstacle analysis line shorter in hopping distance, or I need to make my obstacle analysis line travel towards the source like this. So in place of this obstacle analysis line, I need to make this as the obstacle analysis line. I need to make the obstacle analysis line travel towards the obstacle. Again, it will not be able to find out why the collision is happening, why there is infeasibility. It will again shift it. Now it will find that, okay, there is an obstacle. It now got sighted, and these 2 would be the points. This would be the corresponding line till where my trajectory is generated. Feasible trajectory and a feasible interpolation, a feasible trajectory and a feasible interpolation, both would be constructed. So I need to make my obstacle analysis line travel towards the current state of the vehicle when I find any kind of infeasibility. So this is what this is a nice little flowchart which summarizes all the steps that I have been talking about. The only difference is that sometimes there are big obstacles. I cite them correctly, but maybe it's not possible to reach this point out here via a smooth clothoid curve only because of the shape or the previous position of the vehicle. So in place of directly saying that it's a small obstacle problem and I should move this line like this, what I would be doing is that I'll be carrying out small local optimization. I'll make this point revolve around this small region out here to see if I can make the trajectories feasible. If yes, well and good. If no, then only I'll say that it's a small obstacle problem and my obstacle analysis line or my sweeping line should move towards the current state or it should travel leftward. So there are small local optimizations which are performed. So it looks a very simple graph search algorithm. It looks a very simple thing to do. Where did the concept of lane come in? Unfortunately, the picture that you see out here, that is this shows the smooth clothoid curve. If I do not show the clothoid curves, and if I take in one trajectory like this, or let's say if I only take in the selected points like this, it is a trajectory in the form of crosses, and they go somewhere out like this. It's only that these crosses have been connected by clothoid curves that it looks a smooth trajectory. So I have got two terminologies here. One is the trajectory formed by the clothoid curve, and the other is these crosses which I can connect them line by line only for the sake of discussion. So this is called my trajectory and this is called my lane, which I introduced in the very first slide. The only difference is that the lanes do not have got widths out here, and I can introduce in the concept of widths in these straight line lanes by a very simple phenomena. I say find out the maximum distance after which there is some obstacle or road boundary. So for them it will be this distance, and similarly here it will be this distance. I'll do this for each and every point. Now there are some points which, let's say like this, the distance is too large, and as I said, my lanes would always be under threshold. So I've set out what can be the maximum width of a lane, after which it doesn't matter. So let's say this was this point out here. In place of taking out this complete width, I say this is my threshold distance, and after that threshold distance I limit my lane. So I'll have nice width attached to them lanes. I'll of course only be using this phenomena. I'll not be using the phenomena of lanes. This was just to say how does the concept of variable widths that I presented earlier come into the definition of lanes that we have out here. And the way that I would be using this phenomena, whenever I need to modify the trajectory of a single vehicle, right now there's only one vehicle, so I do not need to do that. Later on we'll be seeing that we'll need to formulate a trajectory and later on change that trajectory. How will I be changing the trajectory? I will be moving these crosses upward or downward. I'll be moving each of these crosses upward or downward, and if I move this crosses upward or downward, naturally my clothoid curves change, which produces my trajectory. So in this figure you can basically imagine if I start pulling and pushing crosses upward and downward, each of these, how does my trajectory changes. This phenomena of pulling and pushing of crosses is what I will be presenting later on when we introduce the concept of coordination amongst vehicles. So these crosses, and for the sake of clarity, the line joining them would be what will be known as lanes in this algorithm. And this nice little graph we've generated based on all those clothoid curves. You can see there are multiple ways out here, because there's a dimension of time that I did not present only for the sake of simplicity. Because of that additional dimension, there's not a single lane, there's not a single trajectory in this region, but there are multiple such trajectories. And as you would expect, when I physically run the vehicle, when I physically run the algorithm, it tries to maximize the separation from all the obstacles out like this. And sometimes there are small obstacle problems that it tries to optimize and find the best way out like this. So that was in all quite straightforward, a quite simple algorithm. For the case of a single vehicle, the essence of the algorithm comes in what I will be presenting in the next slide. And that would be how do we solve the problem of coordination, keeping the same as the problem of planning, or how do we coordinate between vehicles, or how do we plan for multiple vehicles. The general phenomena would be that there would be a road segment that I'm eyeing on, the vehicles will enter. So suppose the first vehicle enters, it constructs this trajectory, it will trace this trajectory. Suppose it's at position here. When another vehicle enters, say here, and it constructs a nice trajectory. Suppose the first vehicle was here, the second vehicle was here, then the third vehicle enters, which itself constructs a nice little trajectory. And I'm dealing with, given these two vehicles, vehicle number 1 and vehicle 2, their current position this and this, and their current trajectories this and this, and their current lanes, which for the two trajectories would be something like this, some courses out here, and for the second trajectory it would be something like this, some courses out here, which for the sake of clarity we draw them as lines. So given their positions, their trajectories and their lanes, how do I plan for this vehicle? And while planning for this vehicle, I'm given a nice little power, I've given a nice little control. I can change their lanes. I can change the lanes of any one of these vehicles or both of these vehicles, and as we know, if I change lanes, they automatically change in trajectories. That's what I said I'll be presenting as the concept of lanes. In this algorithm, I'll be changing in the lanes of the vehicles, and the trajectories would automatically get modified. And as we started out, I'm only trying to solve the problem of definition of a graph. Or for the people who know uniform course search, I'm only trying to say that given a state L, which came up anyway from the space S, I'm only trying to find out the new states. Now I define 3 strategies that will result in my child states, or let's say that I frame in 3 strategies. Each of them would result in one or multiple child states. The first strategy is the same strategy that we saw previously. It's called as the free state expansion, which in the presence of slow vehicle ahead will result in some kind of overtake. So it's also called as the overtaking strategy. And this strategy is responsible for all kinds of overtaking behavior that the vehicle would see. I know in my traffic scenario, if there's a vehicle out here and if there's a slow moving vehicle out here, I can either overtake it. If overtaking is not possible because of some other vehicle coming from the other side, or the road being narrow enough, then I will have to follow it. And that is what I have been doing in every algorithm. This capability was embedded into, which I'll also embed into this algorithm. So that will be called as a vehicle following strategy that will be responsible for generating all plans like this. If it later overtakes, it will be because of the free state expansion of a later state. The third thing which I'm introducing here is something that was inspired from a British kind of traffic, where we have got roads like this. Some people park their vehicles like this. And these are British traffic, of course, is organized, so they are 2 lanes traffic. The problem is that in this kind of scenario where there are 2 parked vehicles, suppose I enter out here, and at same or little earlier some other vehicle enters out here. I'm traveling like this, I'm traveling like this. Now we both cannot simultaneously try to overcome these parked vehicles while they are static. We'll collide out here. Humans naturally gesture each other, talk to each other, use horns, some kind of etiquette, see which one is waiting. Here, also the vehicles can, in our algorithm, the vehicles can talk to each other and decide what to do. The thing is that I will have to embed in this kind of, this vehicle waiting in for this vehicle, or this vehicle waiting in for this vehicle, this kind of behavior I'll have to embed into the algorithm, and all such kinds of plans would be generated by this strategy, which is called as the wait for vehicle strategy. There are multiple scenarios in which one vehicle has to physically wait for the other vehicle to cross through. And now I'll be showing in some results. So if you have followed the algorithm till this level, it's reasonably good. I'll be taking in the intrinsic details very later upon. So there's a small video, the only video that I'll play. This is the overtaking strategy. The blue vehicle overtakes both these vehicles. And this is a very simple strategy where they all parallelly place to each other, so there's no overtaking. It's a simple parallel placement. Now it cannot overtake because of this vehicle, and immediately it overtakes. I'll pause in for a second here. That was the vehicle following strategy. Here there are three vehicles. There's a narrow region out here, a narrow kind of bridge out here. Red vehicle obviously can go because it was generated first. Now the blue vehicle, what you'll see in the video later on, will wait for the red vehicle to cross. It'll then cross, and the green vehicle will wait for the. It's already waiting for the red vehicle, but it'll also wait for the blue vehicle. And look at it, they took a nice position out here, not waiting out here or in some region where the red vehicle finds its odd. And right now you'll see the blue vehicle going and then the green vehicle going if I play. So the blue vehicle goes out here and then the green vehicle goes out here. And this is all the random things that you can generate multiple vehicles, and they all show nice little behaviors. These are vehicles generated only from one side and they all overtake. Some are overtaking, some are following, and then here they are generated from both sides. Some are following, this is following and this is the overtaking. So that's all what basically the algorithm is all about. I'll take in the next few slides, I'll only take in the details of the three expansion strategies, which I've only said that they were the expansion strategies. The first is of course the free state expansion, which results in all the overtaking behavior, which is exactly what strategy we have been following except for this state out here. Now if I see an obstacle, I say that I can avoid it like this. I'll also have to consider all the vehicles which are going in this region. Earlier I simply placed myself in the center, or if the space was too much, then a little on either of the sides. Now I'll have to consider how many vehicles are passing through this simultaneously or near simultaneously when I'm traveling. That's the only change I will have to make, and for each of these vehicles I'll have to do something. So basically what my strategy says that I have got my vehicle out here. Suppose this is its current position. There is an obstacle out here. Let's say there's a small obstacle out here. It uses its obstacle analysis line and it happens to be out here. It says, okay, very well, this is where I want to go. It tries to come out here. Now, while it tries to come out here, for the sake of just as a convention, let me say that the vehicle that is actually being planned is called as my vehicle Ri. So there's a vehicle Ri which is trying to go out here. Simultaneously, there's another vehicle which was previously going like this. Now this vehicle, I need to do something for this vehicle. That it needs to be informed that this vehicle is trying to go in the same region, and now I'll need to divide this space equally, basically I'll have to distribute this entire space available here into lanes for these two vehicles. So that's my first problem that I need to solve. That now the vehicle, for the sake of convention, let me say this is the vehicle RJ. So now my vehicle RJ cannot travel like this. It will have to use a modified trajectory which is wide enough like this. And later on, let's say that it can, after this vehicle has completely crossed, it can go towards whatever it was doing. Now, the problem is that RJ has a modified trajectory, it has a modified lane. A modification of RJ may affect any other vehicle, or let us say there's another vehicle RK. Earlier RJ and RK were in consensus with each other. They were nicely traveling each other's, they nicely knew about each other. RK was traveling like this. Now RJ has shifted up like this, so there's something that RK needs to do. Maybe it needs to find out a new trajectory like this and later on do whatever it was doing. So basically what I'm trying to say is, if any vehicle which is being planned Ri decides to go into a region or a pathway or an area between the obstacle, I need to find out the vehicles which are planning to go in the same region, which will be in the same region at nearly the same time, and need to modify their lanes and correspondingly their trajectories. That's one part of the problem. The second part of the problem is that modification of any of these RJ vehicles can further subsequently cause collisions with any other set of vehicles, say RK. And of course, this looping problem, that if I modify the trajectory of RK, there might be a problem, there might be a vehicle RL which also gets affected, which is now into a dangerous state with vehicle RK. And if I change in the lanes of RL and correspondingly the trajectory, there might be any other vehicle. They might not all be on the same side. There may be some vehicle, say vehicle 1 out over here. RJ was changing its lane and then correspondingly doing whatever it was doing, but now vehicle 1 which was traveling like this, now these two are into problem. So I need to find out all these vehicles which are affected by what? Affected by RI entering into this region, directly or indirectly. I need to find all such vehicles, and let me say that this vehicle set is H. All the vehicles which are directly or indirectly affected by RI coming into this region, and correspondingly I need to find out something else which will be helpful for me later on. I need to find out this entire region, let us say S, which gets affected when RI enters into this region. So now unfortunately I do not have a nice graphic out here, but let me just try to say this was any general road. My vehicle RI planned to come out over here, and all the vehicles that were at this side, they were traveling somewhere like this. They all saw vehicle RI coming like this. Now they'll modify their trajectories like this. So they will come to new lanes and they'll return to the old lanes. So there's a region in which going away from the old lanes and returning to the original lanes is happening, and that region I called as S. H are the vehicles which are affected by the vehicle RI entering into this region, and S is the total areas or the total separation along the road that all these vehicles require to change their state, to change their lane and then come to new lane. And that I have, in how to calculate H and S in a very broad sense, I have tried to put up in this nice little flowchart out here. So basically I need to calculate H and S. My H initially consists of only of the vehicle RI. So I see whether the motion of any vehicle in H in the region S, it results in some kind of collision, some kind of vehicle being affected, some kind of vehicle which is affected. I find out if any vehicle is being affected. So basically I start up with a very small narrow region which only consists of the region in which the vehicle RI is traveling. I start up with a very small H and I basically grow my state H and S as I keep on adding vehicles which are affected. So I check if any vehicle is being affected. If any vehicle is being affected, I add that vehicle into my state H, and the corresponding region I add it into S. I have a grown H and a grown S. And then I see if any of my new vehicles in this grown H is affecting any of when traveling inside this region grown S is affecting any new vehicle which is outside H, which is traveling anywhere. Then I grow my H and S still further by adding a new vehicle. So calculating my new grown vehicle will be my problem 1. Calculating whether a vehicle is affecting the other vehicle will be my problem 2, which I'll be taking in the next few slides. So let me call this problem 1 and problem 2. And I know after all this is over, I've got my H and S. All I'll need to do is to see this region out here and to distribute this space in between all the vehicles edge. This will be my problem 3. I'll be distributing the space between vehicles. I'll be calculating the modified trajectories. I'll be calculating the modified lanes. So these are the 3 problems that I'll be dealing for this strategy. So very quickly, this is my problem number 1, where I calculate the modified region. I, for simplicity, take only 2 vehicles, which is the vehicle Ri, which is the vehicle being planned. It was trying to enter into some region which may have some obstacle or some road boundary at the 2 ends. I had a vehicle Rj. Now Rj now knows that Ri is coming into some region, so it will immediately try to change its lane and occupy the new lane position. So let's say traveling in this region is not helpful for RJ right now, so it will immediately at the earliest, whenever at the earliest it can change the lane, it will try to do so. It will stay in the modified lane as long as it wants. Now Ri and RJ can have very similar speeds, they can have very different speeds. I need to take into account all such possibilities. So RJ cannot try to move into the original lane here, because then these two will happen to be in collision. RJ cannot try to enter into the original lane out here, because say this vehicle was very slow moving while this vehicle was moving very fast. When RJ is here, this vehicle might be only here. It similarly cannot return back to its original lane out here, because let's say Ri was very slow moving. So when it's here, my vehicle RJ is here, but when it is sufficiently ahead of the current state of the vehicle Ri, now it can move. It will at least be having a positive speed. So the graphic that is generates it, I am dealing with the vehicle moving from my parent state L to my new state. Any vehicle Ri, which was originally say using this lane, now it will immediately change its lane, and when it is nicely ahead of the parent state, it will do whatever it was doing previously in this region. And of course, when S was expanded as a graph search, it would have already been decided what's the best to do in that state for this vehicle RJ. So this would be my new state, which will be this will be my by what amount my area S will grow, and that is what I have got a slightly better graphic out here. So there are 2 scenarios which are possible, that RJ, by effect of which the area S is being modified, or which is the new vehicle I have find out is affected by Ri moving from some point say to some point here. So here you see that RJ immediately tries to get a new lane position. It continues to do so, and when it is completely ahead of when it is completely ahead of what is the final position of this vehicle, it returns back to its original lane. And I have grown RJ by a small amount because there was the vehicle RK was somewhere around here. Now this separation would get very small, so I have left in some distance for that as well. So this is my new affected state S2, and similarly is the side when they are traveling in opposite directions, which is what I presented in the previous slide. It will immediately try to change its lane to a new lane. I have not yet told how this new lane will be calculated. It will try to keep this new lane till it is sufficiently and appreciably ahead of the current position of Ri, or let's say the current state of Ri in the graph search, and then it will do whatever it was trying to do earlier. If this was the best position, suppose Ri was basically traveling like this, and suppose Ri was traveling like this, this is how it came through. Say this was some small obstacle, and my vehicle RJ, it was planned to be like this before I decided to make this kind of expansion. So it will return to its original lane like this as soon as it is appreciably ahead of Ri, of the current position of Ri. Now this is how I calculate my affected region. I have all these, that's what I have shown, that I calculate when earliest can I make a change and when earliest can I return. That was problem 1. Now I'm at the problem 2, and my problem 2 says that I changed the lane of a vehicle RJ from something like this to something like this. I calculated the new region, which is S2. Does this change affect any third vehicle RK, which was my problem 2, and that is what I would be trying to solve in this particular problem. Again, there are two cases: when RJ and RK are traveling in the same direction and when RJ and RK are traveling in the opposite direction. This is my affected state S2. Now it has returned like suppose they are traveling in the same direction. I again need to take in account of all the possible speed combination of RJ and RK. The worst case would come when this has a speed of nearly 0 and this has any fast speed. In which case, when RJ reaches the state out here, it has RK has barely moved, and this is when the least separation between RJ and RK would be recorded. If this least vertical separation, or if these hang on, it is this, if this least longitudinal separation that these two vehicles are recording, if it is more than what I desire, if this is if it is sufficiently high, then I know that this vehicle does not affect this thing, or there's no need of placing these two vehicles in separate lanes. They can occupy the same lateral position. Of course, it will do something interesting later on. So there's no need of distributing these two vehicles by this snapshot into different lateral positions. So I don't have to say this will occupy this lane and this will occupy this lane. By the snapshot given to me, they have sufficient distance when the least distance is recorded between them, and if they are traveling in the opposite direction after RJ reaches out here. Now I cannot similarly say, suppose this one has a very large speed V, they'll obviously collide, and they would always if this has a very large speed, then there would be a need to make both these vehicles lie in the same different lanes, which is what I cannot do. I cannot say that all the vehicles moving in this direction would need to occupy a separate lane right now. So I basically use approximations. I know the speed of this vehicle. I say when this vehicle travels this much, which means it changes its lane, it traverses a new lane, and it again comes back into its original lane. When it does all these interesting things, this is what this vehicle would have traveled. I do not know these exact positions, I do not know this exact time, but I know the speed of this vehicle. So I say this is what maximum it would have traveled, which is proportional to its distance, and my lowest longitudinal distance would be recorded out right at the end when this vehicle is here and this vehicle is here. If this is more than the required threshold, if this is large enough, then I'll say these two, the RJ does not affect RK. They have sufficient longitudinal distance. There is no need to change them, place them in different lanes. But if I do not have the required distance longitudinally along the length of the road, I will place them at separate lanes. So though that was problem 2. where the question, of course, problem 1 was to decide how much of region is affected. Problem 2 was to decide, based on the solution of problem 1, whether do vehicles require separate lanes or not while Ri travels to the new region. My third problem is, which is problem 3, that given the set H of vehicles, including the vehicle Ri, which is the vehicle being planned, which by default are lying at, let's say, this position, and my Ri, which is the vehicle being planned, intends to come at this position. How do I move these vehicles? Firstly, so what lane allocation do I do? Like in this case, it will be something like this. In different cases, it will be something else. And then once I've allocated the lanes, when I've done some lateral distribution between the vehicles, once I have told each and every vehicle which is the new lane that you would be occupying, which is the new lateral position, I can easily construct in trajectories which say will be this for the first vehicle. If my second vehicle was here, it will be this for the second vehicle. It will be something else for the third vehicle. So my major problem is this distribution. Now, three cases arise. Like in this case, I can already see that all these I'll draw in the new figure. Suppose this is the road, and this is ideally where my first vehicle is going, and this is ideally where my second vehicle is going, where this distance is more than threshold. And ideally, my red vehicle needs to come somewhere like this. Now we can see that all the vehicles have the required distance threshold, which is more than the threshold of lateral separation that they ideally would have imagined. Now there's no need to move other vehicles. The second scenario is, in the same scenario, this is my first vehicle, this is my second vehicle. They all have very, very large lateral separation. My red vehicle, my Ri, or the vehicle being planned, intends to come out here, but they are, let's say, there's another vehicle which requires the independent speed lane, which by default is out in this lane. Or my red vehicle intended to be out here, it wanted to be out here, but there's another vehicle at this lateral positions. Whenever I say lane and lateral position, they mean the same thing. All that I'm doing is that in my region S, which is something like this, I calculated H, and I'm trying to divide this road between H lanes. So I'm basically trying to divide my region S into H lanes, and then I'll say that they all occupy one vehicle each. So if this is the normal thing, now we know that while all the vehicles have the required separation, which is more than the threshold, which is more than what they would be liking, these two vehicles do not, and the solution is very simple. If I move this vehicle out here, then and this vehicle a little out here, then all the vehicles have more than required distance, they have more than required separation, they have more than required lateral separation that they would have liked. There is no need to move this vehicle and this vehicle and this vehicle by any amount. The third is, when there are too many vehicles, suppose there are three vehicles out here and this is a very narrow road, or there are two obstacles like this. Now the maximum that none of these vehicles can occupy the largest possible separation, that's out of the equation. So I basically see what is the entire separation available, and I distribute them equally amongst all these vehicles. So my objective 2, which was to state that if separation is more than desired, each vehicle tries to make the minimum most lateral movement. That's out of the equation now. The vehicles do not have the minimum required separation available laterally. So I go by distance maximization equation, and I maximize the separation between the vehicles. And this is from a more practical, the examples that I showed, this is what I was actually simulated. There are two vehicles out here. This is the vehicle being planned. It sees this vehicle ahead out here. This is the obstacle analysis line, so it does see this obstacle. It states that this vehicle is being affected by the motion of this vehicle out here. So it's the minimum required distance, or the minimum separation was not available. So it says I will lie here. This is the new separation for the blue vehicle out here. So this small separation that was available to me has been equally divided between these two vehicles out here, and that's what you see. My blue vehicle, which was at this position, it immediately changes its position. It immediately occupies in the new lane position which it was directed. It crosses out at this point, and now it says that it is sufficiently ahead of this vehicle which will be out here, so again it again comes to its new lane back ahead. So I'll just reset the graphics to show you one interesting thing, that while planning for a vehicle which is here, what I've done, I basically pushed all the lanes out. I have pushed in the trajectory of blue vehicle out here. Blue vehicle earlier had this trajectory, now it has a slightly pushed trajectory, and has a slightly pushed trajectory because I'm assuming my vehicle RI will start from here. It will take this position, but after this position it will suddenly get evaporated. It will suddenly get outside of the scenario, and that's what the pushing effect is out in this trajectory. The vehicle RI, which is this vehicle out here, it occupies this position and suddenly evaporates. It suddenly goes away, and therefore my blue vehicle, it returns to its original trajectory, trying to maximize the separation. It corrects its lane, it comes to its original lane. Now people understanding graph theory and graph search and uniform graph search would appreciate the fact better that in reality, of course, my vehicle would not evaporate here, it will not disappear here. That is a problem that would be dealt by a later expansion when I try to expand this new expanded state, where it will try to expand this layer, it will try to expand the trajectory even further. So I had a nice little blue vehicle's trajectory out here because I added a new fast moving vehicle out here. So part by part, in the first expansion it will try to push this trajectory, in the second expansion it will try to push this segment of the trajectory till the overtake is complete, and that's exactly what simulation I showed in the results section. So that was the free state expansion, which is the longest and the most boring one. I'll go very fast from now on. The second expansion is very simple. It just states that whenever you see a vehicle in front, so suppose this was my vehicle RA, which is the vehicle being planned, this was the road, it sees this vehicle ahead, and it basically needs to take care of both the possibilities of overtaking this vehicle at the same time. Following this vehicle, I've already shown how does it take the possibility of overtaking this vehicle. I have to show the other part, how does it take the possibility of following this vehicle. So I select the closest vehicle ahead, and I simply say that the speed of this vehicle Vi equals to, suppose this was the vehicle RJ with traveling with speed Vj, I reduce the speed of this vehicle to the speed of this vehicle. So I simply say Vi equals to Vj, or now I'll only need to reduce its speed. So find the closest vehicle and reduce its speed. That is the only thing that I have to do. The way the previous expansion search strategy worked, the way that it was finding in obstacles, the way it was finding in vehicles, it was changing the lanes of the vehicles, it was changing the trajectory of the other vehicles, it was doing all sorts of things. Similar thing I'll be doing with this strategy. The only difference is with this reduced speed. So this is entirely as was presented later on. The only little tweak in the algorithm that we actually saw later on, that if there was an obstacle out here, it used this as the obstacle line, it later reduced its speed. Now reducing speed, actually the traversal distance of the sweeping line is basically proportional to the speed. So reducing this thing meant new obstacle analysis line. As a result, what was happening that earlier this vehicle tried to go like this, now it with a reduced speed it wanted to go like this. So this was my vehicle being followed, this was my vehicle which was being followed, and this became the trajectory of my vehicle being planned for. So I'll draw in a new graphics just to be clear. So when we followed this strategy presented so far, what was happening that this vehicle saw this vehicle ahead, which is going out here, and it decided to follow this vehicle, but in following this vehicle, it took this route. Now, this is clearly not following this vehicle, because following this vehicle means that I will be going at this side of the obstacle or in this region and not this region. So that's why there's a simple tweak that has been applied, that my obstacle analysis line does not change. And this is what nice little graphics that I have produced, that this is my obstacle analysis line. It saw a vehicle ahead which was out here. It decided to follow it. It reduced its speeds. Reducing speeds meant that the distance between the or my sweeping line distance will reduce, and in this case you can see it reduced its speed drastically. It reduced its speed by a very large amount. That's why my distance became extremely short, and that's what trajectory it produced. In this new trajectory, it's best to be at this position. It's at the center of the road. That's what it did. And my last strategy in this set, which is even more simple, I will be taking in a wait for vehicle strategy. So I earlier showed a nice little result section where there was a narrow bridge ahead. There was a narrow bridge on the road. There was some road segment. There were vehicles out here which wanted to cross the bridge, and there was a vehicle being planned out here, and this vehicle needs to wait for all these vehicles out here. So that's what I would be dealing with in this strategy. I'll show you how that result was produced, or what strategy produced that result. Now the algorithm, as you would imagine, is very simple. I need to decide which vehicle I need to wait for. After this vehicle crosses the bridge, I'll simply follow. I mean, I'll simply do whatever the later expansion strategy says, but I need to decide which vehicle I need to wait for. After I've done this thing, my strategy is very simple, that I need, so I'll draw in some graphics out here. Suppose this was a narrow bridge. There were some vehicles out here. I say that let me wait for this vehicle. In practice, what we'll be doing, I'll be deciding whether I wait for this vehicle. I'll use this as a child state. I'll basically use all the forward calculation for the waiting for this vehicle. I'll do the same thing for this vehicle. I'll do the same thing for this vehicle. I'll do the same thing for this vehicle which might be ahead. So out here you can say that the one of the possible strategy will be that this vehicle crosses and then I cross and then these vehicle cross. I'll use this as a strategy. The other strategy, I'll try to expand using this strategy. The other strategy would be that this vehicle crosses, then I cross, then these two vehicle crosses. I'll be computing for that strategy. I'll be computing for all sorts of strategy. So that is the first problem, which is deciding the vehicle that I need to wait for. The second is that I need to decide whether I wait here, whether I wait here, whether I wait here, whether I wait here. So exactly where to wait for. Suppose I'm in the center of the road, I cannot stand tall like this. These vehicles will have to pass by. Each of these vehicles will have to pass by. So I either wait here or I wait here or anyone here. So this is my second problem, that I need to compute where do I wait for. And we know, because it's a problem of multi-vehicles, that I added a new vehicle to the system. So I need to modify the trajectories of each of these vehicles to account for this vehicle waiting. And that's all. Once I know the modified trajectory, I can easily formulate this as a graph node, as a graph state in the graph that I'm producing, and that will be all. So in the next slide, I'll basically be dealing with this problem, which is a very good problem, which states how do I compute this, which is a very simple and the good problem. How do I compute out of these states? And then I'll be dealing with the problem of modifying these vehicles trajectories, which will be a very simple problem indeed. So the first problem, or the problem of computing the point of wait. Suppose I have my bridge like this. I am standing tall right here, and these are some vehicles either on the bridge or off the bridge. Suppose I'm solving for waiting for this vehicle. Now I see that if this vehicle does not do anything, then it is the rightmost vehicle, and if this vehicle does not do anything, it is the leftmost vehicle. In practice, I see this region not so much earlier, but I see them in the critical region out here, which will be the region where my obstacle analysis line is formed. So I see the rightmost and the leftmost vehicle. A good strategy would be to leave the threshold distance, which is the largest separation as per the algorithm modeling, and to wait out here. If it collides with the obstacle, then of course strategy 1 cannot be followed, then I'll have to maximize for the separation. The second strategy can be to do the same for the rightmost vehicle. This is the occupancy of the rightmost vehicle, or this is the rightmost occupancy of the rightmost vehicle. I leave the threshold distance or the maximum separation, and then I wait here. Whichever requires minimum deviation, I'll select that point. So again, I presented two heuristics right at the start. I'm using the same heuristic to solve this problem, which is the problem of computing the point of weight. Once I've computed the point of weight, I obviously need to modify the trajectories of the other vehicle, which is very simple. Suppose I have got vehicles out here. Suppose I've got my bridge out here. Now, different vehicles might be doing something very different out here, but then the problem is my safety distance or my position of weight is based on that the vehicles do not cross this line of the rightmost vehicle or this line of the leftmost vehicle, whichever the case may be. So in this critical region, or the region where my obstacle analysis line was crossed, I simply cancel all overtaking behaviors and I straighten their trajectories, I straighten their lanes. So if any vehicle was doing anything fancy out here, changing its lateral position and everything, I simply cancel it up, I straighten the lane till it has crossed this region. So in this region, the vehicles can only travel straight. And of course, because there are multiple vehicles, I'll have to do this for multiple vehicles. Now there's one thing which algorithmically is of a lot of interest to me. I'm modifying traffic. I'm modifying the vehicle dynamics till some time. Let's say till time t. Now I need to calculate this time t, which is the time. Suppose this is the bridge. I'm waiting for the second vehicle out here, and I'm waiting at this position. Now I need to know when does this vehicle cross this vehicle and the motion of this vehicle can continue, which is the time t. I need to calculate this vehicle, and for this it is extremely necessary that I plan for this vehicle number 2 out here first. Once I modify the trajectory of this vehicle, I get this time t, and I modify the trajectory of all the other vehicles, which is a vehicle this and vehicle this. I straighten their trajectories, I cancel anything interesting that they are doing, I straighten their lanes only till this time t, after which they are ready to do whatever they were doing earlier. So that's all for my this expansion strategy. And there's a change in convention here. Earlier, in all these vehicles, the vehicle being planned was at this side. Now the vehicle being planned is at this side. So you'll have to arrange accordingly. The vehicle being planned, which is Ri here, it saw this thing. It said that let me keep an option of waiting for a vehicle out here. There was a vehicle Rk which is out here. I computed this critical region out here. I straightened the trajectory of Rk out here, which you see it as a trajectory out here, and this was decided as the point of waiting. Basically it was going this thing. I kept the threshold distance and I decide the point of wait here, and I simply connected via a clothoid curve, and Ra will simply wait for this vehicle till Rk crosses. And that's a part of the simulation that I showed previously. So I have 3 expansion strategies for every lateral, for every state. I'll use all these 3 expansion strategies, each one of them, the obstacle avoidance strategy would normally generate two states for either left of an obstacle or right of an obstacle. The vehicle following will always generate in one state. The wait for vehicle will generate states depending on the number of vehicle traveling in the other side. Now it becomes too many states for a single state. Each one of these will expand in further states. So we know that it becomes too many states to expand. The basic mantra behind my approach was that I'll be expanding the minimum number of states. I did well. It was a continuous pace. I discretized. I got rid of a lot many states. But the problem, so out of infinite states possible, I've only I only have these very few number of states possible, but it's not good enough. I need to further reduce my number of states. And hence I say that earlier I said for every state I'll be expanding using all these three strategies. I changed that. I'll be selecting which strategy to use. So I embed in some heuristics in deciding which strategies to use. And the first heuristic I embed is something from a naturally observing behavior. Once we decide, due to any reason, that we need to follow that vehicle, overtaking might not be allowed, overtaking might not be feasible, then we always follow that vehicle. We don't say that I'll first follow you and then suddenly I'll overtake you. Similarly, if we overtake a vehicle, we always overtake it. We don't change our decision later on. So that's one heuristic that I would be using, that once I decide to follow a vehicle, the vehicle would always be followed. And once I decide to overtake a vehicle, it would be overtaken. And of course, how we know that's that we were maintaining state H. My state H would basically enable me to decide, was this vehicle being followed or was this vehicle being overtaken. The simple catch here, of course, is that many times we have got scenarios like this, where in what I showed in the simulation results also, this vehicle cannot overtake this vehicle because of this vehicle traveling in the other side. This overtaking trajectory is not possible. But after this vehicle leaves, I have gotten a scenario where this vehicle is out here and these are the two vehicles out here, this nicely following this vehicle. Now overtake is possible. So an overtaking, once infeasible, can later become feasible only when a vehicle joins or it leaves. These are the only two scenarios possible. Either a new vehicle comes in or an old vehicle goes away. So I'll complete my statement now, that once I decide to follow a vehicle, I will always follow it, and once I decide to overtake a vehicle, I will always overtake it, unless a vehicle comes and goes away, in which case I consider both the possibilities. So basically, even here maybe the road was too narrow and overtake is still not feasible, so I'll consider both these possibilities. This is my first heuristic. Of course, we are not taking the cases where road suddenly widens up and overtake is now feasible. The second is wait for vehicle. As I said, that it's always marked by narrowing down of road. It's always when the road suddenly becomes narrow because of a narrow bridge problem, because of parked vehicles problem or anything, then is the only case when I'll be considering the strategy of wait for vehicle. So this enables me to decide which of the three strategies do I use for expanding my states, and I obviously need to do some analysis every time I add an obstacle, or let us say when I was going with two obstacles, these were the only possibilities. When I added a new obstacle, then basically my options increase. I can now take this route, at least theoretically it's possible. I can take this route or I can take this route. So as my obstacle increase, my states would exponentially increase. And of course, because we know that after I calculate this, I'll have to calculate this, and after I calculate this, I'll have to calculate a fresh sample of this. So my number of states which result in some kind of division in strategy out here, they also increase, and my general states also increase. And for every vehicle, that was for static obstacle, if I have got a slow vehicle ahead, it can either be followed or be avoided. So in a similar way, that for every vehicle I can either follow or I can overtake it. So as my number of vehicles increase, my number of decision making points where I need to decide between overtaking and following, and my normal states where I simply need to follow that strategy, they also increase. Now that's all for the presentation. I'll briefly go to the result video, which you can basically enjoy now in a much better fashion. I'll again show you in how the various strategies are happening, in what are they practically doing. So again, this is the overtaking strategy, what I have shown. How is this made possible? This is the parallel placement strategy, which is nothing but it's like the static obstacle avoidance. This is the vehicle following avoidance. We know now what happens, and we know that how this is calculated. So those three results are, of course, the three strategies, and those were the results that were typically catering into exactly those strategies ahead. These are more generic results which involve a mixture of strategies, and that will be all for the presentation. And thank you.